In this video, we will learn what an alloy is. We'll learn about some common alloys and how the composition of an alloy influences its properties and therefore its uses. An alloy is a mixture of at least one metal with one or more other elements. The other elements can be metals or non-metals. We said an alloy is a mixture. It's actually a solid solution of elements dissolved in each other. Now, almost all metals around us in our everyday lives are alloys and not pure metals. So how do we get a solid solution mixture of a metal with other elements? Let's take the example of steel production. A metal, in this case iron, is heated. When it reaches its melting point, it liquefies. The liquid iron can then be mixed with other heated and liquefied metals or with non-metals, for example with carbon. Carbon from coal is added. This is all mixed together in the blast furnace, and a liquid mixture of iron and carbon is produced. Sometimes other treatment steps are performed, and then cooling and solidification is allowed to occur, and we end up with an alloy of iron and carbon, which is a solid solution mixture of the elements iron and carbon. And this is steel. Now, this is a very simplified description of steel production. The topic of steel is covered in more depth in another video. The melting, mixing, cooling and solidification process that we have described is one of the common ways to produce an alloy. There are other methods where powdered metals and other powdered elements are mixed together, pressed and hot rolled. It is important to remember that an alloy is not the same as a compound. In a compound, the components are present in a specific ratio. But in an alloy, the components can be present in potentially any proportion, just like with other mixtures. But let's ask ourselves, why alloy metals with other elements? Pure metals are often not useful in real-life applications. For example, iron in its pure form is actually quite soft and rusts very easily. But by alloying iron with other elements, in other words, mixing it with other elements, for example with carbon to produce the alloy steel, results in a material that has combined or new properties to that of its components. Steel is much harder than pure iron. Alloying changes the properties of a metal. We could say that alloys have combined or new properties compared to that of their individual components. The changes in properties that result from alloying include changes in hardness, strength or toughness, changes in malleability, ductility, electrical and thermal conductivity, as well as magnetic properties. Alloys are usually much harder and stronger than the pure metal. Alloying is very useful because these new properties can be purposefully adjusted or controlled to produce a material that is just right for a certain application. In other words, we can tailor-make the properties of materials. Let's have a look at some common alloys. 3 types of steel are mild steel, tool steel, and stainless steel. Mild steel with a low percentage of carbon is quite malleable and is good for use in molding car bodies. Tool steel contains a higher percentage of carbon plus usually other elements like tungsten. This makes it very hard and tough even under high temperatures, which is perfect for use in high-strength tools such as hammers and drill bits, which undergo a lot of friction during their use. Stainless steel usually has a relatively high percentage of chromium as well as other elements like nickel. These prevent this steel from rusting or corroding. Surgical equipment like scalpels as well as cutlery for eating are usually made from stainless steel. It's important to remember that a higher percentage of carbon makes steel stronger, but also makes the steel more brittle because it is less malleable. Duralumin is a common aluminum alloy, made largely of aluminum and a little bit of copper with other metals. It is low in density and lightweight because of the aluminum, but is very strong because of the other alloyed elements, making it perfect for use in building aircraft parts. Brass is the name given to copper-zinc alloys. These are usually mostly copper with added zinc. Brass is more malleable than copper and zinc alone and is corrosion resistant. It is perfect for use in plumbing parts. Solder is a tin, lead and zinc alloy. It melts easily but sets quickly and is also corrosion resistant. Solder is used to join electronic components. The melting point of a particular solder depends largely on the content of tin. The relative proportions of copper and zinc in brass affect the properties of a particular brass, and the aluminum and copper ratio in duralumin will influence the density and strength of the material. Can you see that the percentage of the components in an alloy directly influence the properties of that material? And these percentages can be changed. Let's look at one last example. Gold jewelry is not made from pure gold. It's usually an alloy of gold, silver, zinc, and copper. The composition of a particular gold alloy will affect the strength of that gold material, as well as the color. Exactly how does alloying change the properties of a material? In solid pure metal, the atoms are arranged in layers and rows, bonded by metallic bonds. The layers can slide over each other when a force is applied. Only a relatively small force is needed to do this in a pure metal. That is why pure metals are generally soft and rather malleable and ductile. However, when a different element is mixed or alloyed into the structure, there are usually atoms of different sizes. The arrangement of the atoms becomes distorted. It is more difficult for atoms to slide over each other, and a much larger force is needed to move these atoms or slide layers. This is why alloys are usually stronger and harder than the pure metal. Though these diagrams are drawn in 2 dimensions, remember that in reality the atoms are arranged in 3 dimensions. Let's have a look at the 2 ways in which the added element atoms can arrange themselves in the original metal. An interstitial alloy is when the added element atoms are small enough to arrange themselves in the holes of a metal lattice. Small atoms that can do this include hydrogen, boron, carbon, and nitrogen. A substitutional alloy is when the added element atoms substitute for some of the original or parent metal atoms. This can happen when they have a similar size. Examples of atoms that can do this are nickel and chromium atoms in amongst the iron atoms in steel. Some alloys are mixtures of interstitial and substitutional arrangements. And remember, there are still distortions in the arrangement in reality, although this has not been shown here. We mentioned that the properties of an alloy depend on the relative proportions of the components. We can plot this kind of information on a graph. Let's have a look. Let's imagine an alloy consisting of elements A and B. The relative percentage of A as to the percentage of B can be changed, and this will result in different properties for the alloy. This particular hypothetical graph shows how the content or percentage of element A in the alloy influences the strength of the alloy, and the strength is measured in megapascals. These kind of plots or graphs are very useful. They allow us to identify the optimum compositions of an alloy for a particular property. As we saw, the particular property being investigated here is strength. So what is the optimum composition or content of element A needed for maximum strength in this alloy? Well, the maximum strength is the highest point on the curve. In this case, almost 450 MPa. Going down to the corresponding point on the x-axis, we see that a content of 16% of the element A is needed to achieve this maximum strength in the alloy. And if we say 100% minus 16%, we get 84% being the content of element B needed to achieve this maximum strength. Notice also that on this part of the curve, the strength actually begins to decrease with contents of A higher than about 16%. While on this part of the curve, when the content of element A in the alloy is less than 2%, the strength of the alloy is not at its lowest, although the percentage of A is very low. The lowest strength of the alloy occurs when the percentage of A is approximately 2%. At this point, the strength is about 100 megapascals. Lastly, let's imagine we wanted to make an alloy of elements A and B that had a strength of about 300 megapascals. If we go across to the curve and down to the x-axis, we'd need to make our alloy with a minimum of 8% of the element A and the rest element B to achieve this strength. The key word here is minimum. Truthfully, any content of element A from about 8% up to about 20%, which is the maximum content value we've been given on this plot, would give us a strength higher than 300 megapascals, more than we needed. It's not necessarily a problem to make an alloy that is stronger than is needed, but we'd need to consider other properties at different strengths. For example, brittleness. We'd have to look at a brittleness versus content plot as well. Now it's time to summarize everything that we have learnt. We have learnt that an alloy is a mixture of at least one metal with one or more other elements, and that alloys are actually solid solutions of metals with other elements. We learned that alloys have combined or new properties compared to the properties of its components, and that alloys are often harder and stronger than their original elements. We looked at some common alloys including steel, which is an iron-carbon mixture, duralumin, which is an aluminum-copper mixture, brass, which is made of copper and zinc, as well as solder and gold. We saw that the proportions of the components directly influence the alloy properties, with a specific example in steel being that a high concentration of carbon increases the strength, but also the brittleness. We learned that alloying disrupts the atom arrangement in a metal, and this is part of which gives alloys their unique properties. And lastly, we looked at a brief hypothetical example of an alloy property versus composition plot, and saw that this is a useful tool to identify optimum compositions of alloys and predict the properties of a desired alloy.